Object-oriented modeling tries to take concepts in a problem space and model them in a piece of software. Given how complicated a problem can be, we need to refine our models through design principles: abstraction, encapsulation, decomposition, and generalization. Each of these principles requires you to make a decision on how they apply to your system. What attributes and behaviors do you need to model in a class through abstraction? How are these attributes and behaviors grouped together and accessed through encapsulation? Can my classes be simplified into smaller parts using decomposition? Are there common things across my objects that can be generalized? These principles are meant to guide the choices that you make when designing an object-oriented system. Some design decisions will be easier to make than others. For example, a car can have attributes such as color, make, and model. It has behaviors like acceleration and steering. The car can be decomposed into its parts, like engine, transmission, and battery. But how does everything relate to each other? Can we generalize any parts of the car? Generalization and inheritance are some of the more difficult topics to master in object-oriented programming and modeling. While inheritance is a powerful design tool that can help you create clean, reusable, and maintainable software systems, misusing inheritance can lead to poor code. That happens when design principles are used improperly, creating more problems than they are meant to solve. So how do we know if we're abusing inheritance? Well, there are a few points to be aware of when applying inheritance. First, you need to ask yourself, am I using inheritance to simply share attributes or behavior without further adding anything special in my subclasses? If the answer is yes, then you're misusing inheritance. This is an indication of misuse because there is no point for the subclasses to exist, since the superclass already is enough. Let's say you were designing for your favorite pizza restaurant. You need to model all the different varieties of pizza that the restaurant has on the menu. Given the different combination of toppings and names you can have for pizzas, you might be tempted to design the system using inheritance. The pizza class has been generalized to know what toppings it will have, its size, style of crust, and how long it will take to cook. This seems reasonable, but let's look at why this is a misuse of inheritance by examining the code for a subclass of pizza. Despite the fact that a pepperoni pizza is a more specific kind of pizza, it is not really different from the superclass. You can see that the pepperoni constructor uses the pizza's constructor and adds toppings using the pizza's method. There is no reason to use inheritance in this case, because you can simply use only the pizza class to build a pizza with pepperoni as a topping. The second indication of improper use of generalization is if you break the Liskov substitution principle. The principle states that a subclass can replace a superclass if and only if the subclass does not change the functionality of the superclass. How would this principle be violated through inheritance? Let's take a look at this example. This is our generalized animal class. It knows how to eat, walk, and run. Are you able to see how we can introduce a subclass that would break the Liskov substitution principle? What if we had this type of animal? A whale doesn't know how to run and walk. Running and walking are behaviors of land animals. The Liskov substitution principle is violated here because the whale class overrides the animal class's running and walking functions and replaces them with a swimming behavior. The whale no longer behaves in the way we would expect its superclass to behave. An example of bad inheritance can be seen in the Java Collections library. Have you ever used the stack class in Java? A stack is understood as first-in, last-out data structure. It has a small number of well-defined behaviors like peek, pop, and push. This is not the case in the Java stack class because the stack class inherits from the vector class. This means that the stack class is able to return an element at a specified index, retrieve the index of an element, and even insert an element into a specific index. These are not behaviors expected from a stack, but because of poor use of inheritance, they are allowed in Java. If inheritance does not suit your needs, consider whether decomposition is more appropriate. A smartphone is a good example of where decomposition works better than inheritance. A smartphone has characteristics of a phone and a camera. Here is one design. It does not make sense for us to inherit from the phone and then add camera methods to the subclass smartphone. We should be using decomposition to extract out the camera's responsibilities and put them in their own class. The smartphone now indirectly provides the responsibilities of the camera and the phone through separate part classes. The smartphone does not need to know how these classes work. Inheritance can be a difficult design principle to apply, but it is still a very powerful technique. Inheritance lets you define subclasses that are tailor-made for your system, while defining common attributes and behaviors in the superclass. Remember that a common goal is to build reusable, flexible, and maintainable systems. Inheritance is simply one technique to help you reach that goal. It is important to understand that a technique is beneficial when used properly, but can cause headaches if not.